let's go through this. An ideal gas initially has pressure 1.0 times 10 power 5, volume 4.0 times 10 power negative 4, and temperature 300 Kelvin as illustrated in figure 2.1. So you can see the flow chart to understand it. And then, okay, so after that, what you see here is there is an increase in pressure. Okay, the pressure increase from 1 times 10 power 5 to 5 times 10 power 5. Volume remain. Temperature, we need to count it out. A change in energy of the gas of 240 joule result in an increase of pressure to a final value of 5 times 10 power 5 at constant volume. So, for example, in what situation the pressure will heat up? I mean the pressure will increase. For example, if you heat up, you supply energy to heat up the gas, and then the gas will have greater pressure. And it has no change in volume, maybe because you put in a container. So the gas cannot change in volume. So the thermodynamics temperature becomes T. Calculate the temperature T. Okay, so we can count it straight away for this. This is quite direct. Since they give pressure, volume, and temperature, we use general gas equation. This formula, let me substitute. Divide by volume, 300. Pressure, divide by T. Okay, then you get the temperature. Now the amount of gas means N, the number of mole. Okay, so we can use PV equal to nRT. So let's say I stick to the initial state. You either use initial state or final state. It's up to you. Use either one. Don't mix. Okay, so you will get the same answer after all. So PV equal to nRT. Pressure, then volume, and then N, R, and then T. So you will get N 0.016. Okay, now let's move on. The increase in internal energy delta U of a system may be represented by the expressions delta U equal to Q plus W. So this is the first law of thermodynamics. State what is meant by the symbol positive Q. Positive Q means heating or endothermic. Positive W is work done to the system. Like the atmosphere is pressing the solid liquid gas. Part 2, state for the gas in A the value of delta U. And Q and W. Okay, so we start from the easiest one. You know, W equal to P delta V. But we obviously see that there is no change in volume. No change in volume, so we should expect W to be 0. The second one, Q. So Q, you can see here, there is a heat supply, which is here 240 joule heat supply. So the positive Q should be 240. 240. Huh? Delta U. So imagine 240 plus 0. Delta U should be 240. Okay. Now let's move on. Next question. State what is meant by the internal energy of a system. So sum of random distribution. Random distribution is the keyword. Huh? Sum of random distributions, keywords, of kinetics energies and potential energy of all molecules in a system. Okay, part B. Explain by reference to work done and heating whether the internal energy of the following increases, decreases, or remain constant. Okay. The first one, the gas in a toy balloon when the balloon bursts suddenly. Okay. So let's start with the volume of gas. Volume of gas obviously increases. You know, initially the gas all stuck in the balloon. Now the balloon bursts. All the gas can come out. Okay, all the gas can come out. Then the volume increases. It's greater than the volume of the balloon already. Volume increases. Balloon bursts. Volume increases. Volume increases. So if you still remember, our formula is W equal to P delta V, which is P initial minus final. I said like this to make it easier. So then, volume increase means final is greater than initial. So you should expect change in volume to be negative. Negative, huh? Okay, so we say that first. Negative. So that means this is work done by gas. Okay, W is negative. First thing. Okay, second thing, we need to talk about the E. The E, yeah. So a balloon burst, it doesn't involve heating of balloon. It just bursts like that, So no heating of gas. E equal to 0. Okay. Then delta U equal to E plus W. So internal energy decreases. Okay. Now next one. Ice melting. So melting, you think of E is positive. It's an endothermic process at constant temperature and at atmospheric pressure to form water that is more dense than the ice. So again, it comes to a situation where water is more dense than the ice. So more dense means their volume decrease. Their volume decrease. Volume decrease. Okay, and if you look at the note just now, just now they said in the note just now we have a partial question also, where we assume the change in volume is too small until we ignore it. So it's up to you. Both will be accepted. Okay, so you may say volume decreases. You may say volume decreases a little bit. Volume decreases a little bit, or you can also say uh, no change in volume. That will be just fine. Okay. Now let's say lah. Okay, let's say since initially I already said there is no change in volume. So work done is negligible because change in volume is small. Okay, so W is 0. Second point, heating of ice during melting so Q is positive. Okay, delta U equal to E plus W. Okay, this one I use E. Hence, internal energy increases. Okay, so they also accept if you write like this, the first point. First point you say work done by the system because volume decreases. W is positive. So if you write this, is okay also. After all, that is clear enough. W is positive, E is positive, then delta U is positive as well. So accepted also, the blue color one. Okay, now let's see a bit more. This side. What is meant by internal energy? So you can just refer to the question just now for the definitions. I look at part 2 straight away. The basic assumption of the kinetic theory of gases that leads to the conclusion that there is zero potential energy between the molecules of an ideal gas. So potential energy is about the spacing. The spacing is due to the attractions, forces of attraction, or the intermolecular forces. Okay, so the kinetic theory say that there is no internal, no forces or attractions. Okay, so we can say that no force of attractions or repulsions between molecule. Because of that, potential energy in ideal gas is assumed to be zero. Yeah, so I have to remember this. This is how we should explain it. And then Okay, part B. The pressures P and volume V of an ideal gas are related by PV equal to 1 over 3 nm C square, where n is the number of molecules, m is the mass of a molecule, and c square is the mean square speed of the molecule. Using this equation to show that the mean kinetic energy Ek of a molecule is given by Ek equal to 3 over 2 kT, where K is the Boltzmann constant and T is the thermodynamic temperature. Okay, so we have to show this. PV equal to nRT, and they give PV equal to 1 over 3 nm C square. So we can equal them. Arrange. Boltzmann constant is Avogadro over mole. I purposely put it to the bottom. No, this is actually number of molecule over number of mole. Number of molecule over number of mole is Avogadro constant. It's Avogadro, not Boltzmann yet. Not Boltzmann yet. So I change it to Avogadro first. Okay, Boltzmann constant is R over Na. R over Na is Boltzmann constant. Then divide by 2. Then I get half mc square equal to 3 over 2 kT. So Ek equal to 3 over 2 kT. It's the proving of formula. Okay, now let's continue the question just now. After proving the formula, the question said, a cylinder contains 17 grams of oxygen gas at a temperature of 12 degrees Celsius. The mass of 1.0 mole of oxygen gas is 32 grams. It may be assumed that the gas behaves as an ideal gas. Calculate for the oxygen gas in the cylinder the mean kinetic energy of a molecule. So that means they expect you to use the formula just now. Ek equal to 3 over 2 kT, 3 over 2 times Boltzmann constant. You can check the data booklet on the front page. This is the value. Temperature in Kelvin, 12 degrees Celsius plus 273. Okay, then you will get 5.90 times 10 to the power of negative 21 joule. So that's the answer. Part 2, the number of molecules. Number of molecules. So, okay, we already have 17 gram and the relative molecular mass 32. So we get the mole first. Mole equal to mass over molar mass 32. So once you get the mole, number of molecules equal to mole times Avogadro, so equal to 17 over 32 times 6.02 times 10 to the power of 23. This is Avogadro. Then you will get 3.20 times 10 to the power of 23. Okay, so now the total internal energy Okay, total internal energy okay, so we use this formula. Internal energy equal to potential energy plus kinetic energy. Okay. Ideal gas, as you can see. At the beginning of the question, we already said ideal gas has no forces or attractions, and because of that, we can say that there is no potential energy. In A part 2, we already explained accordingly. Zero potential energy. So it is 0 for potential energy. And then for kinetic energy, so kinetic energy, how we count it? We have information here. One molecules have this amount of energy, and you have so many molecules. So we times to get the total kinetic energy. Okay, so we times. Take the number of molecules, multiply with the energy of one molecule. Okay, then we get 1890 joule. Okay, so that is the answer.